Today we study about system software and simplified instructional computers architecture, okay, and its version. So before that, we see the introduction of system software. So system software consists of variety of programs that supports the operation of a computer. We'll write it here. Consists of variety of programs. Variety of programs that support operations of a computer. So as we know, we used different types of system software. Also we write programs in high level languages like C++ or Pascal. Okay. So we write these programming languages using a text editor. Okay. So text editor mainly used to create and modify the program. Okay, after we write these programs, we translate the programs into machine language. So using a compiler. So here comes a compiler. So the role of compiler is what? Translate the programs into machine language. And then we'll use this machine language program. We load into memory using linker or a loader. Then the resulting machine language program was loaded into memory and prepared for execution using loader or linker. So in between compiler and this loader or linker, we use another concept called debugger. For what? To detect errors in the program. To detect errors in a program. So initially we use text editor to create and modify the program, and after then we will go for compiler to translate these programs into machine language, and finally the resultant machine language program will be loaded into memory and preparing for execution. So if there is any error happens in the compiler, so we will call the debugger to detect the errors in a program. Okay, so now we see simplified instructional computer SIC version. So this has two versions. The first one is the standard version, that is SIC itself, and the second one is XE version, extra equipment. So we will write like this: SIC extra equipment, SIC XE. Okay, so now we see simplified instructional computer, SIC's machine architecture. So in this machine architecture, we see the concepts like memory, registers, data formats, instructional formats, addressing modes, and sixth one is instructional set. The seventh one is input and output. So memory, register, data formats, instructional formats, addressing modes, instruction set and input and output. Okay, the first we see memory. So the memory consists of 8 bytes. Okay, the memory consists of 8 bytes. Okay, so as we know that any 3 consecutive memory form a word. Okay, so which means 24 bits. We'll write that also. Any 3 consecutive bytes form a word that is 24 bits. Okay, so all the addresses in SIC will be byte addresses. That is one important. All addresses on SIC are byte addresses. We define byte addresses here. Okay, and in SIC memory, the maximum memory limit would be 2 power 15. 2 power 15 bytes. This is the maximum. Whereas in SIC we go for 2 power 20 bytes. Okay. So 8 bits of data we use, and any 3 consecutive bytes form a word that is 24 bits. In SIC machine architecture, we will use only byte addresses and the maximum limit would be 2 power 15 bytes. Okay. Now we will see registers. Second one, registers. Okay, we have 5 registers in SIC. The number 1 is accumulator. Accumulator is defined by A and its number is 0 and its use is for arithmetic calculations. Arithmetic operations we write here. Okay, and the second one would be index register. So index register is defined by X, its number is 1, used for addressing. And the third one is linkage register. Defined by L, number is 2. So like for example, if we have J sub, so the functionality of J sub could be jump to a subroutine. So we'll write here jump to subroutine. So that is the instruction, jump to subroutine instruction. Used to store the return addresses in the register. Okay, return addresses in this register. That is the use of linkage register. And we have fourth one is program counter. So it contains the address of next instruction to be executed. Okay, so program counter, so contains, so this is defined by PC. Okay, it is defined by the number 8, contains the address of next instruction, stores the return address in the register. Sorry, to be fetched. So I have written the earlier one, to be fetched for execution. Okay, so the program counter defined by PC, it is defined by the number 8. So it contains the address of next instruction to be fetched for execution. Okay, and the fifth one is status word. So it is defined by SW Okay, so contains a variety of information including the condition code. Informations including the condition code. So we'll see the format of status register: mode, state, ID, condition code, mask, X and I code. This is interrupt code. So this is the format of status register. We'll see each one of the functionalities. And this mode refers to user mode, or we are in the supervising mode. So user mode or supervising mode. If we are in the user mode, it denotes 0. If it is in the supervising mode, it denotes 1. Okay. And this refers the status, whether the process is in the running state or ideal state. Okay, process, checking whether the process is in ideal state or running state. If the process is in ideal state, it sets to 1, or if it is running state, it sets to 0. Okay, and this ID refers to process ID. Okay, and the CC would be condition code. So tells whether the devices is ready or not. So we'll write it here. This tells, CC is a condition code. This tells whether the device is ready or not. Okay, and this masking is an interrupt mask, and X is nothing but unused bit. So refers to unused bit. Okay, and finally this I code is nothing but interrupt code. Okay, that is we'll call the interrupt service routine if there is any interrupt occurs. Okay, so that is called I code. Okay, so next we'll study about data formats. Okay, we have integer format, and next one is character format and negative format. Negative values in integer. Okay, so integer, it stores integer values as 24 binary numbers. Okay, stores integer values here. The values. And for negative numbers, we use 2's complement here. This is one of the important concept in SIC and SIC architecture. Very interesting. Okay, so for negative values, we use 2's complement. Okay, characters are stored, their 8-bit ASCII codes. Characters are stored using their 8-bit ASCII codes as usual. ASCII codes. And one main important thing in the data format on SIC is here it will not use floating point. Not use floating point. Okay, I mean no floating point is used in SIC machine architecture, where SIC HC uses this floating point technique. Okay, so this is all about the data formats in SIC. Now we'll see instruction format. Okay, so all the machine instruction on the standard version of SIC is a 24-bit format. Okay, so the standard version on SIC, all the machine instruction is 24-bit. Okay, the format would be like this: opcode, X, address. So opcode hold 8 bits and X hold 1 bit and the address hold 15 bits. So totally we'll have 24 bits. Okay, and this flag X is used to indicate index addressing mode. Okay, indicate index addressing mode. If it is an indexed addressing mode, then the X is set to 1. If it is not, it will be set to 0. Okay, that we will see in addressing modes. So next one we are going to study about addressing modes on SIC. Okay, so there are two addressing modes here. One is direct addressing mode and another one is indexed addressing mode. Okay, if it is a direct addressing mode, the format of the instruction format X is set to 0. If it is an index, it is set to 1. Okay, so we'll write that here. If it is if it is a direct addressing mode, X is set to 0, then we'll have the target calculation is directly an address. So target address will be a address. Okay, if it is an indexed addressing mode, now the X will be set to 1. Okay, then the target address calculation would be target address is equal to address plus contents of X. Okay, and this parenthesis indicates the contents of memory location or contents of a register. Okay, I do say this parenthesis of X, parentheses are used to indicate the contents of a register or a memory location. Okay, and this target address is calculated from the address given in the instructions. Okay, so target address, I will write this target address, okay, is calculated from the address given in the instruction. Okay, so if it is a direct addressing mode, you will have the target address as address. Or if it is an indexed addressing mode, you will add the contents of register or a memory location to the address and you will finally get the target address. Okay. Now we'll see an example here for direct addressing mode. Okay. Direct addressing mode. So if we have an instruction like LDA 10. Okay, LDA load accumulator. Okay, if the label 10 is in the location 1000, okay, how do we write in the format? So we have to draw an instruction format here, that is opcode. Okay, and then we'll have X and then address. Okay, so opcode, LDA's opcode value would be 00. See here, LDA's mnemonic code would be 00. So it holds how many bits? 8 bits. So we have to write 0004 and next 0000. So 8 bits. Okay. So this is a direct addressing mode. Then X is equal to 0. Okay. We will write 0 here. And the 10, the label is in the location. If it is in the location 1000, so how do we write? It holds 15 bits. Okay, and this opcode holds 8 bit and here 1 bit and this address would be 15 bits. Okay, so we have to write accordingly. So we will write 00004 and next 0000 and next would be what? 0, 0, 0, 0, 4, 8, 12. Okay, and again you will write 1. How do we write 1? 0, 1. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and one more 0 is needed. Okay, 15. So now totally 15 bits. So we have to group it now. So 4, group like 4. So 4 bits 0, and this 4 bits 0, and here it is 0. Okay, so we have to group like this. So I'll write one more time here 0, 0, 0, 0, 0, 0, 0. Okay, and here x will be 0. And now, because I have already drawn a table, so it is something congesting. I mean, nothing. Okay, here, now we'll write from here 0, 0, 0, 0, 4, 0, 0, 0, 0, 8, 0, 0, 0, 0, 12. Now 1, 0, 0, which means the binary value would be 1. So since it is a 15 digit, so we have to remove this 0 and write the rest 3. Okay, so now we have to combine this as 4. Okay, 0, and from here to this one is 0. This is 1 and it holds 3, and we'll combine this to 1, and rest of the things 0, 0, 0. Now the object code for LDA 10 would be what? 0, 0, 1, 0, 0, 0. Okay, so this is how we'll go for direct addressing mode. Now the effective address would be, target address would be what? 1000. Okay, this is the target address. Okay, and we'll find object code like this. Okay, here LDA 10, the target address would be 10. Okay, therefore we write here contents of the address 1000 is loaded into the accumulator. Okay, so now we'll see the example for indexed addressing mode. Okay, so we'll take an instruction stch buffer comma x. We'll draw the format now. Opcode x address. Okay, so now opcode. Opcode of stch would be, we'll see opcode of stch is here 54. Okay, so we'll write that. Opcode of stch. 5 is 0101 and 4 would be 0100. So this is opcode for stch. X is a part of an instruction, so it is an indexed addressing mode. We set x to 1, and now the address of buffer would be 1000, in the sense the effective address would be what? 1000 plus contents of x. Okay, so we'll write here 1000, in the sense we have to hold 15 bits. Okay, so in that how we have to write 1, 2, 3, 4. Okay, 1, 2, 3, 4, 8. 1, 2, 3, 4, 12. 1, 0, 0. If the buffer's location is 1000, so it would be what? 1000. Okay, if it is set to 1, it is 1, and here it is 5, this is 4. This is an indexed addressing mode, so it is 1, and we go for 1000. Directly the effective address would be what? The target address would be 1000 plus contents of register. Okay, so the contents of index register X is added with the effective address, and that's how we find the target address. Okay, so we'll write it here. Contents of the X would be the what? Contents of the index register X. Okay, So now we'll see instruction set. We have 5 instructions on SIC. Okay, so the one would be load and store instruction. Okay, so this is used for to move or store data from accumulator or memory. So we have what? LDA, STA, load accumulator, stored accumulator, and we go for register like LDX, STX. Okay, the use would be what? To move or store data from accumulator or memory. Okay, that is the load and store instruction. And the second one would be comparison instruction. Comparison instruction. And this would be what? We go for an example COMP. Okay, so used to compare data in a memory by the contents in the accumulator. That's how we compare. Okay, so also we write here used to, all such things we'll write, used to compare data in memory by the contents in accumulator. Okay, and the third one would be arithmetic instruction. As we all know, arithmetic instruction used to perform what? On arithmetic operations on accumulator and memory, and thereafter store the result in accumulator itself. Okay, so we'll write here arithmetic instruction used to perform arithmetic operations on, you can write arithmetic operations on accumulator and memory. Okay, and store the result in accumulator. So for example, we say add. Add is an instruction. Sub, mul, div, all such things. Okay, and next one is conditional jump instruction. Okay, so this will do compare the contents of accumulator and memory and perform the task based on the conditions. So like JLT, JEQ, these are all conditional jump instruction. Okay, JLT, JEQ and all conditional jump instruction. What does it do? This will compare the contents of, we'll write here, compare the contents of accumulator and memory, once again, and perform task based on conditions. Okay, and the fifth one is subroutine linkage instructions. This instruction is related to subroutine. We have J sub, R sub. Okay, so this will do what? Instruction related to subroutine. Return the subroutine, jump to that particular subroutine, we go for J sub and R sub. Okay, and the last one is input and output. Here in input and output, each device is assigned a unique 8-bit code. Okay, we have 3 instructions, each of which specifies the device code as an operand here in input and output. Okay, so we'll write here each device is assigned to a unique 8-bit code. Okay, and there are 3 instructions here, 3 instructions of IO. Okay, and each of which specifies the device code as an operand. Okay, those 3 instructions are TD, RD and WR. Okay, so this is a test device, read data, write data. Okay, so read data from the device. Here this instruction tests whether the device is ready or not. If the device is ready to send or receive, so we can read the data or we can write the data. Okay, so like if it is less than, it symbolizes the if it is less than, it means that the device is ready to send or receive the data. If it is equal to, it means the device is not ready. Okay, which means what? The device code is, if it is less than the device code, which means the device is ready. Which means the device is ready. Okay, to send or receive. And this equal to symbolizes device is not ready. Okay, if the device is ready, then we can go for read or write operations. Okay, so these are all the 3 instructions which is available in input and output. So we have studied system software introduction, and we studied SIC machine architecture, comprises of 7 features, the memory, and the second one is a register. Okay, we have seen 5 registers which is available, and the status word format. Okay, and the third one is data format and instruction format, fourth one, and the fifth one could be addressing modes, and we have 2 addressing modes, direct addressing mode and indexed addressing mode. Okay, we have seen with an example, and the 6th one is instruction set, and the 7th one is input and output. So in this we have 3 instructions, test device, read and write instruction. Okay.